Okay, Italo, I'm not sure where you joined us, but we're about halfway through the talk. The first talk has been taped, so you can see it. I'm going to put it on my YouTube channel after this class, okay?
Great, thank you.
Okay, so as I was saying that we are now looking at this experiment. This experiment was to see if UVC light could induce denaturing in DNA, because we need a mechanism for replication of DNA in the Archean when the complex enzymes did not exist. So this was the absorption spectrum that we found, and it's exactly what we expected. We have a peak absorption at 260 nanometers, which, by the way, is exactly where the peak in the light which was coming into the Earth at that time was centered. It was centered at 260 nanometers. Okay, so that's another very interesting coincidence. Not a coincidence, we claim. It's actually dissipative structuring, which gave this structure of DNA the ability to absorb at 260 nanometers, where the intensity of the light in the UVC was maximal. Okay, and so then we measured for a constant temperature how light, UVC light, could induce denaturing. And we find that every time we turn the light on, the absorption goes up. That means we have a denaturing, because this is the hypochromic effect between double-strand and single-strand DNA. When you separate the two strands, the absorption increases, the light absorption increases. And that's what we're seeing every time we turn the light on. So the light, in fact, is denaturing DNA. And these were the curves as a function of wavelength, for the different wavelength. How important was the denaturing? Okay, and so that brought us then to this curve, which is the temperature dependence of this light-induced denaturing. So after about 60 degrees centigrade, light-induced denaturing becomes very strong. And this is in percentage denaturing per hour, okay, on the y-axis. And this is a function of temperature. Okay, so how in fact is light denaturing DNA? Well, what we assumed at first was that it was just a thermodynamic effect, that you have ultraviolet light coming in, being absorbed on one or two of the bases. Sometimes it's absorbed on two bases, a single photon on two bases, but usually only on one base. And then this electronic excitation energy gets dissipated into heat very quickly. And so we assumed that, let me see if I can do this. I might get into trouble here, if we don't lose it. Claudette? Okay, there you see the simulation. Okay.
Yes.
So we assumed that this light would come in, get absorbed, and be converted into heat. And then the question was, well, how many base pairs would this heat affect such that we could get denaturing? And so knowing the specific heat of water, knowing that a photon of 260 nanometers gives about 4.8 electron volts of energy, we can calculate the diameter, which would result in an increase of about 3 degrees centigrade due to this one photon of 4.8 electron volts. And we did the calculation, and it turns out in water, the diameter is about 4.9 nanometers, or about 16 base pairs. So one photon would be enough to increase the temperature about 3 degrees centigrade for about 16 base pairs. So next, what we decided to do was the Monte Carlo, the molecular dynamics simulations, to determine if this is really possible. And what we found, I have a student, Adriana, who did these calculations. What we found is that the heat actually gets dissipated to the water very quickly. So unless there was a mechanism for heat being directed along the axis of the DNA, it would be very unlikely that just because of the heat, we could get denaturing. So what other mechanism is possible? Well, one mechanism which is possible is light-induced proton transfer. So if you absorb a photon on a base, you can also produce a transfer, for example, of this hydrogen atom, which is really a proton. Now this hydrogen changes from this base, which looks like adenine, to this base, which is adenine dimina. And then we'll get like what is in the center diagram here. I lost my pointer, that's why I'm losing it. In the center here we are. We see that this hydrogen atom has been transferred from the adenine to the thymine. And what does that do? Well, that changes the charge distribution here. And a lot of the strength in the DNA between the two strands is due to this interaction between base pairs, which are piled one on top of the other. So if you change the charge distribution, you're also going to be changing the interaction strength between the two strands. These are from two different complementary strands. It actually becomes even worse than that, because you can also get another transfer, another proton transfer. So this is two proton transfer from the same absorption event of one single photon. And that changes the charge distribution even more, and therefore the stacking between the bases gets reduced. The interaction between the stacking gets reduced, and therefore the DNA becomes more vulnerable to denaturing. So we think now that this is actually the process. We haven't looked at it in too much more detail, but this seems to be what the process giving rise to photon-induced denaturing is about, is this light-induced proton transfer between the bases. Okay, so the idea then is that the photon comes in, gets absorbed on one or two of the bases, and then some of the energy is distributed over that part of the DNA. But we also have an effect which is called a mechanical effect. If this occurs on the last two or three bases, then we get a fraying of the ends. So the ends of the DNA start to wander about separately. And that gives rise to stronger force for denaturing. So for example, if the photon was absorbed on one of the bases in the middle of the DNA, we wouldn't necessarily get denaturing, because, well, the bases will come apart, but then they would join back up very quickly. But if it occurs on the ends, then we have a much greater chance that the bases will not rejoin themselves. So it's probably a combination of the two effects. One is this light-induced proton transfer, and the other one is the fraying of the ends in the base, in the DNA structure. Okay, so the future then is to try to have this whole process together, like in a PCR experiment, in which we have only ultraviolet light impinging on the DNA at a given fixed temperature, let's say a little bit less than 85 degrees centigrade. And we have a slight cooling in the night, or we turn the light off at night, and that allows the bases to find complementary segments and to form a second strand. So this experiment is still to be done for all of them together. But as I mentioned before, this part of the experiment has already been proved in the laboratory. And we have proved this one in the laboratory. So we really have a mechanism now for light-induced denaturing. And the important point about this mechanism is that it ties replication with dissipation. And as I said, for anything to occur, any irreversible process, we need to show that we are dissipating, because the process occurs only to dissipate. That is the fundamental thermodynamic function of any irreversible process, including life. Okay, now this is the final part. Here we come to the homochirality. We know, for example, that molecules, especially if they have a carbon atom, can come in two forms, which are right or left-handed. So these are very similar, but one is just the mirror reflection of the other. So it's like our two hands. We cannot superimpose our two hands on each other, but they are the mirror reflection. And all of these molecules which have a carbon atom, which is called an alpha carbon atom, and give rise to three-dimensional molecules, can come in two different forms, right or left-handed. This here is for amino acid. But the same is true for DNA. We can have right or left-handed DNA. But it turns out in nature that almost all of nature is right-handed. We have right-handed DNA, and we have left-handed amino acids. And so this has been a puzzle for a long time, and it's been very difficult, and it still really hasn't been explained. We think we have an explanation, and this is what I'm going to give to you today, but it's still to be tested in the laboratory and to be confirmed. But the idea is rather simple, that the light from the sun is not polarized. But before getting to that, I should say that how do you specify what is right and left-handed? By the amount of light which is circularly polarized right or left-handed that the molecule absorbs. So if it absorbs more right-handed circularly polarized light, then we call it right-handed molecule. And if it absorbs more left-handed circularly polarized light, we call it left-handed. And so what is circularly polarized light? Well, you know that light has vibrations of the electromagnetic fields. So we have the electric field vibrating in one plane and the magnetic field in the other plane. Now, usually normal light is not polarized, so we have all kinds of angles of vibrations. So we have a mix of vibrations. But if we put a polarizer here in front of the light, then we can get light which is only vibrating in one plane, and that's called plane polarized light. Now, if that light is internally reflected from a material, then we can get what is known as circularly polarized light. That is, we still have light which is vibrating only in one plane, the electromagnetic field only in one plane, but it's now rotating as light is propagating in a particular direction. So we get like this spiral effect. We get vibrations around the spiral. And this is called circularly polarized light. And how do we get that? Well, we can find it on the ocean surface. And in fact, the ocean surface is the region in which the greatest amount of circularly polarized light exists on Earth. And it's very close to the surface. So what happens is that the light comes in from the sun, which is unpolarized. It gets refracted at the air-water interface. And then it scatters of material. It could be a water molecule, or it could be some impurity in the water. And that scattering process produces plane polarized light. And that plane polarized light, if it is internally reflected, so if this angle is very small and we get total internal reflection at the air-water interface, then we can get circularly polarized light. And it turns out if you put the instruments to measure this circularly polarized light at the ocean surface, you will find up to about 5% of the light coming from the sun is circularly polarized. Now, this circular polarization changes from the morning to the afternoon, depending on the direction of viewing it. But if we maintain the direction, this is the person looking at it, if we maintain this direction, then in the morning, for instance, we can get left-hand circularly polarized light, about 5%. And in the afternoon, when the sun is in this side, we will get right-handed circular polarized light. So we get a difference between the morning and the afternoon. Now, DNA also has this interesting feature, which is called circular dichroism. And that means it absorbs a little bit more right-handed circularly polarized light compared to left-handed circular polarized light. So this is the graph. When it goes below 0, this is just the difference between left and right-handed absorption of the light for the molecule. This is for DNA. This is life-created DNA. We find that we get a little bit more absorption of right-handed circularly polarized light, and that's why DNA is called right-handed circularly polarized. And this occurs about 260 nanometers also. So these are the curves for different DNA samples. So for instance, the black sample is this large or long DNA segment. The blue is the small one, and this red here is adenosine with tryptophan. So this is including an amino acid with the base. And we see that when the amino acid is included with the nucleobase, we get in fact much more circular dichroism. That means that it absorbs much more right-handed circularly polarized light than left-handed circularly polarized light. So this is over the whole spectrum, but now we have to normalize it. So we have to do a convolution with the light spectrum, which was arriving at Earth's surface during the Archean. And this is this dotted line here. And we also have to do it with the absorption spectrum, convolution with the absorption spectrum of DNA, which is the solid line. So if we do the convolution of these two spectra with these circular dichroism spectra, we get this diagram, which is on the right. So this is just the same, but with a convolution. So we see the effect is pronounced because, in fact, this is where light is being absorbed most prominently, just where the dichroism is more important. And after about 280 nanometers, there is no more UVC light coming in at Earth's surface in the Archean from the sun. And that's why at 280 nanometers, it goes to 0 when we do the convolution with these absorption and the amount of light coming in the Earth's surface. So therefore, we have this very interesting effect, which is that we get different amounts of circularly polarized light, left or right-handed, depending whether it's in the morning or the afternoon. Let's say in this case, we have excess right-handed circularly polarized light in the afternoon. Now that is interesting. You can say, well, how does that relate to denaturing, and how will that relate to getting only right-handed circularly polarized light, which is right-handed circularly polarized DNA, which is what is called homochirality? Well, that is because, as I said, that we can produce denaturing. No, so to produce new DNA, we need denaturing because that's part of the replication. If we don't have denaturing, we're not going to have replication. And so we will not get further production of the DNA. So if this mechanism of light-induced denaturing was operating during the Archean, and it was a temperature-dependent effect, as I showed in this graph at the bottom here. As the temperature goes up, this light-induced denaturing also increases significantly. And because of the fact that in the morning, the temperature of the ocean surface is colder than in the afternoon, and in the afternoon, we get only right-handed circularly polarized light, or only an excess of right-handed circularly polarized light, then we can see how we can get the symmetry breaking, and we can get reproduction of only right-handed DNA, because it's more probable that right-handed DNA will be denatured because it absorbs more right-handed than left-handed light, and there is more right-handed light in the afternoon. Okay, and where the temperature, we could do the same for the morning, and we will get more left-handed, but the trouble is that in the morning, the temperature is lower, so the effect of light-induced denaturing will be less. So through this mechanism, acting over many days, because each cycle is 1 day, we can get homochirality. And we can do that calculation just by assuming, for example, the number of left-handed DNA of a particular size. It doesn't matter for right now what size it is, but we do this recursion relation so that the number in a given generation is equal to the number in the previous generation times a factor, and this factor includes the amount of light-induced denaturing, which could be either from right-handed light or left-handed light. but the one from right-handed light for right-handed DNA will be more prominent, and the one for left-handed DNA, left-handed light, will be more prominent in the denaturing. So we can calculate what the number of left-handed DNAs will be based on the number in the previous generation and some factor which accounts for this light-induced denaturing. So these PLR, for example, is the probability of a right-handed photon absorbing on a left-handed DNA, etc. No, for the other ones. And this parameter C here, this factor C, is just a parameter which measures the quantum efficiency for denaturing. That is how probable it is. So let's assume that it's very low, no, about like 0.001. That it means it takes 1,000 photons to be absorbed on DNA before it denatures. That will, of course, depend on the length, no, and on how important this light-induced denaturing mechanism is acting, no. But this is a safe bet. This is being very conservative, saying that we only get denaturing if 1,000 photons are absorbed. And if we assume that we have a 5% excess of right-handed circularly polarized light in the afternoon, for example, at the ocean surface, we get an excess maximum of about 5% in the afternoon. And if we assume that we have like a 0.07% dichroism difference, so this is this graph here, we're looking at this difference here of the absorption between left and right-handed, and it is about 0.07%, so it's small, but it's non-negative. It's not zero, sorry. Okay, and let's just assume that we have no denaturing in the morning because the ocean surface temperature is too cold for denaturing, let's say. And we assume we initially start with a racemic distribution. That means we have equal right-handed and left-handed segments, components of DNA. And so we calculate the probabilities. You can convince yourself that these are the probabilities here at the bottom right, or sorry, the bottom left. So if we assume that the probability for a right-handed photon being absorbed on a right-handed DNA is 1, then we can calculate what we would expect for these other probabilities in the afternoon when we get this right-handed circular polarized light. You can convince yourself that these are the right expressions. And then we can calculate the chirality, which is just really the difference of left minus right over the sum of the two, and then plot that as a function of generation. In our case, each generation is 1 day because it takes 1 day to complete the cycle of reproduction. Okay, and so if we do that for the different strands, then we can find, depending on the size of the strand, the shorter the strand, the more quickly we get 100% circular, 100% right-handed DNA. But for example, if we do it for DNA plus tryptophan, it would take only about 117 years, which is really nothing in the history of life on Earth, to get 100% circularly DNA with that given circular polarization. Okay, and this is for the other DNA strands. Okay, so then if there's no questions there, any questions? No?
I have a question, but of the previous slide then.
Okay, this one or this one?
The last one. Another.
This one?
No, the one of yes, that.
This one. Okay.
This hypothesis is alternative, or is the accord, I don't know, de acuerdo, with the RNA, RNA world hypothesis?
The RNA world hypothesis, yeah. Oh, that's a good question. Okay, so first, I have been talking really only about DNA. because we did the experiments with DNA. There's a difference, an important difference between RNA and DNA, because RNA has a much lower denaturing temperature. Maybe you know also that for this virus, the vaccines for this COVID virus are made from RNA, and that's why they have to be kept at very low temperature so they don't start destroying themselves, so it doesn't degenerate. So DNA is much more robust. RNA is more vulnerable to disintegration. And so we did it with DNA, notwithstanding the RNA world hypothesis. So this is a hypothesis in which many are in agreement with that the first nucleic acid was RNA and DNA came later. And why do they say that? Well, because RNA has been shown that it can also act as an enzyme for its own splitting and other functions which are important in replication. So that is the main reason why RNA has been considered as the first molecule of life. But there's no other real reason for assuming that RNA was the first molecule of life. In fact, to produce RNA, it's almost the same difficulty or even more difficult than producing DNA through this dissipation, this structuring from precursor molecules with UVC light. So we don't really have an advantage in that case for RNA. But you can imagine that the same thing could be happening also with RNA, but at lower surface temperatures. So this is surface temperature about 85 degrees centigrade is the denaturing temperature of DNA. For RNA, depending on the size of the segment, you would have to go down to about 40 or 50 degrees centigrade. But we could have had on the Earth's surface those temperatures also existing at the beginning of the Archean. Because, for example, in the poles, we would expect colder temperatures than at the equator. So we could have had 50 degrees centigrade, which is the RNA denaturing temperature at the poles, and 85 degrees centigrade at the equator, for example. So it's not excluded that this process could be operating on RNA. And we had always planned to do that as an experiment also, but we just haven't had the time yet. And it's a little bit more complicated because RNA is more delicate. And you have to treat it with more precaution than you do DNA. But well, we could maybe make that. That's in fact one of the chapters in my book, or it's a section, I think, in one of the chapters where I talk about the RNA world and why we think that it was not necessarily the case that life started as RNA and then DNA later came on the scene. That perhaps both of them were being evolved through similar mechanisms at the same time, but in different parts or different latitudes, so at different temperatures. And then at some point they came together and formed a symbiosis, because we need messenger RNA now to propagate or to denature and not to denature, but to replicate DNA. Okay, Claudia? Oh, I think they're gonna try to throw me off again, so I better finish quickly. We're almost finished here. In fact, let me see if I can just get rid of this.
Yes, all fine. Thank you.
Okay. Okay, you can check the chapter in my book, or we can do another class on that. That would be a good class to do about RNA. So then just to summarize, so life then is an irreversible process. And so like any other irreversible process, it has to dissipate a generalized chemical potential. In the case of hurricanes and the water cycle, which are irreversible processes also, they dissipate a temperature gradient. In this case, we're dissipating the photon gradient from the sun. The visible and ultraviolet light coming in and the infrared light being given off to space. So the most important generalized chemical potential is, in fact, the solar photon potential. And it was also in the Archean, the most important generalized chemical potential. That means the potential which was giving the greatest amount of free energy. So light dissipates photons today. We know that in the visible. That is what the chlorophyll molecule and the other molecules are doing. But in the Archean, we are saying that it was ultraviolet in the UVC range, and gradually now it has evolved to dissipate photons in the visible, which is in fact where the greatest intensity is and has always been. So RNA and DNA have this conical intersection, and so do many of the fundamental molecules of life, which means that they dissipate very rapidly and extremely efficiently UVC light into heat. So we have described RNA and DNA as self-organized microscopic dissipative structures. Now we haven't directly shown you yet how these structures can be produced through these photochemical and chemical mechanisms, but that is one thing that Claudette is doing her thesis on, and we'll dedicate another talk to that specific demonstration that these molecules can in fact be formed just from UVC light and some precursor molecules in the environment in water at the surface of the ocean. Now the complexation of antenna molecules, for example, tryptophan amino acid with RNA and DNA, this is like donor acceptor, so we can transfer the energy from the amino acid to the RNA and DNA, and that increases dissipation of the system as a whole. And that is maybe how information began to be stored in the DNA or RNA. So now we have to be in this UVC range at the beginning of life because there was not enough energy to make and break covalent bonds in the visible. And there were, so this in the UVC we do have enough energy to break and make covalent bonds, but in the visible we don't. So that's why life had to start out using or dissipating UVC light, because the visible photons were not enough energy to break and remake carbon covalent bonds. But this energy, this light in the UVC has an energy which is not enough to produce ionization, where you are losing electrons and therefore slowly start destroying the molecule. So the proliferation of fundamental molecules can be explained by this autocatalytic photochemical reactions. That is when they act as templates for the reproduction of DNA. And this UV tar mechanism, this is enzymeless replication consistent with the autocatalytic photochemical reactions which are occurring. So we have done an experiment which is confirmed. UVC light-induced denaturing occurs for DNA, and we have given a plausible explanation of the homochirality, which arises because of the asymmetry in this ultraviolet and temperature-assisted replication mechanism, this UV tar mechanism. Because during the afternoon, there's more right-handed light, let's say in one hemisphere, and so the temperature is greater. So those which absorb more right-handed light would be more likely to denature and therefore reproduce themselves. So gradually we get to homochirality, which is 100% chiral molecules, right-handed DNA. And we also have tied evolution with greater dissipation. And that's the same for any physical process, that evolution occurs only through increasing dissipation. So the system only evolves in such a manner that dissipation is increased for a non-equilibrium system, which we will find in the case of the book of Prigozhin. So these are the acknowledgements of my students. There have been now about 14 students which have been involved in this. And Alex Simonov, who's from Macedonia, who's a collaborator with me, and also Digapa, which has supplied us with money. Thank you very much. They're probably going to cut us off. We only have about 4 minutes remaining. So if you have any questions now, go ahead. I'll just put on this slide, which is to say that I have some money for becas, for trabajo de tesis. Si alguien tiene interés, los requisitos son que deberías de estar en los últimos semestres para que puedas inscribir en trabajo de tesis, que tienes un promedio creo que es 8.5, no, no estoy seguro si no es 8, pero ponemos 8.5 para ser conservador. Y que tienes tiempo para dedicarse al trabajo de tesis. Y si estás interesado, mándame por favor un email y nos ponemos de acuerdo. Si hay muchos estudiantes o más que uno, pudimos poner un pequeño problema para ver quién primero saca el resultado y la mejor resultado para decidir quién. ¿Ok? Entonces, o si conoces a alguien que está en la clase, en el curso, que no estaba aquí hoy, lo menciones, por favor. Bueno, ahorita preguntas entonces. Si alguien tiene preguntas. O sobre qué estamos viendo en el libro de Prigozhin. Si no está muy involucrado, porque no tenemos mucho tiempo ahorita. Tenemos 2 minutos para preguntas.
Disculpe, profesor. Sobre esto puedo leer en su libro, ¿verdad?
Sí, sí, ya es un poco más actualizado aquí, pero la mayoría, la básica sí aparece en el libro, en
Muchas
distintos
gracias.
capítulos.
Sí, estaba checando el segundo capítulo, la parte después de lo histórico.
Ajá,
Me parece que ven unas cuantas cosas que vimos las clases anteriores.
sí,
Y creo que todavía no, bueno, todavía no llegaba como a esta, esta parte del final.
ok. Sí, Andrés, sí, está en el libro. Si tienes unas preguntas, me mandas un email o lo discutimos aquí en la siguiente clase. El experimento también está en el libro y casi todo. Tenemos mejores resultados y esos son, por ejemplo, estas gráficas, estas aquí a la derecha, que no están en el libro. Pero básicamente todo está ahí. Entonces sí, si tienes oportunidad de leerlo, por favor, y preguntarme.
Sí, muchas gracias.
No, a ti, Andrés. ¿Otras preguntas? Ítalo, ¿tienes unas preguntas? Si todavía estás ahí.
Yes, I'm here.
Ok,
Everything all right at the moment.
ok. Claudette?
I think that everything's okay.
Okay, and then, so I'm going to cancel it now because we're just running out of time anyway. We have only 1 minute before they're going to throw us out. So keep reading Book of Prigozhin and my book if you have time. And if you know anybody who's interested in the beca for this is the licenciatura, me comunicas, por favor. Ok. Bueno, nos vemos la próxima entonces en una semana. Cuídense mucho, todavía hay mucho virus que andan afuera.